A group of people steps into a dry riverbed. Beneath their feet is nothing but hot sand, bleached rocks, and absolutely no sign of surface water. One person walks past a stretch of flat sand, ignores a high bank, and stops only at a bend wrapping around a large boulder. Why here? 3 tiny clues have converged. The sediment is finer. A few animal tracks point toward the exact same spot, and a cluster of plants looks noticeably greener at the lowest point of the terrain. The person starts to dig. The initial hole is bone dry. The group waits patiently. Then, drop by drop, water slowly seeps through the sandy walls. The water didn't appear because they dug to some magically perfect depth. They dug in the right spot because they understood exactly what had happened on the surface long before it dried up. When facing the harshness of nature, we often ask the wrong questions. Which tree always points to water? Which bird always flies toward a lake? How deep is deep enough? The right questions are, where does the rainwater from this area naturally flow? What kind of soil can hold it? Where is the absolute lowest point in the basin? Which signs are fresh and which are old? Has this source been maintained by people who came before? And is the water shallow enough to reach by hand? This isn't a single survival trick. It's the process of peeling back 6 layers of information: topography, sediment, vegetation, animals, memory, and the technology to extract and carry it. Before tracking down those clues, we need to distinguish between 4 types of invisible water, because each requires a completely different search method. The first is water trapped in sediment. After a storm, runoff can soak deep into sand, gravel, and silt. The surface of a creek might be baked dry, but a shallow, saturated zone can patiently wait just beneath. These alluvial aquifers store and transmit water through the tiny, empty spaces between grains of sand. The second type is water hidden inside an already known source. This could be a soakage buried under the sand, deliberately covered to keep animals out. It only reveals itself when the top layer is scooped away, requiring the digger to wait for the water to seep back in. To an outsider, it is just a patch of dirt. To someone with local knowledge, it is a lifeline waiting to be reopened. The third type is water held within rock holes, tree hollows, or the roots of certain plants. These sources are intensely localized. The fourth and highly specific type is water that is no longer in the ground, but is currently being carried. A water container made from an ostrich eggshell, a leather skin, or another vessel transforms a single water point into a massive radius of survival. Fragments of eggshells at the Diepkloof rock shelter in South Africa show this tradition dates back around 60,000 years. But beware of common misconceptions. A lush green tree doesn't guarantee water right beneath its roots, as some species send roots down much deeper than human hands can dig. Following animals isn't a foolproof compass either. Animals might travel dozens of miles, drink at different times, get moisture strictly from their food, or rely on salty, muddy water that would make a human sick. Finally, digging deeper isn't always better. The water might not exist, it might be too deep, contaminated, saline, or the deep sandy trench could collapse and bury the digger. Once we clarify the types of sources, the search mechanism becomes much clearer. The water seeker never asks, "Where is the water under the desert?" They ask, "Where would the water that just passed through this landscape be forced to stop?" The first step is reading the entire catchment area. Before looking at a single tree, you have to look at the elevation, the slopes, the drainage lines, the valleys, the foothills, the old riverbeds, and where multiple small channels converge. Geologists note that low-lying terrain and valleys generally have better prospects for shallow groundwater than hills, though the actual results depend on rock structure and sediment layers. Water obeys gravity long before it obeys the footprints of any living creature. The second step is finding where the water is forced to slow down. Water permeates and pools more easily in depressions, widened sections of a riverbed, behind topographical barriers, where sand and gravel accumulate, at the base of slopes, or at impermeable rock outcroppings that force underground currents up toward the surface. The third step is reading the language of the sediment. An ancient water flow always leaves behind layered sand, rounded gravel, fine silt, scour marks, snagged debris, or changes in soil color and compaction. These traces prove water traveled through here, even if they don't promise water remains. The fourth step adds biological data. A cluster of groundwater-dependent plants can signal a shallower water table, a spot where moisture lingers longer, and where roots have successfully found the saturated zone. Animal and bird tracks can narrow the search area further, but only if the observer intimately understands the behavior of each specific species. The fifth step is using memory to pick the exact spot. This is the most crucial layer of all. The group might know exactly which side of the boulder the water rests on, which bank to dig into, what month the source runs dry, and exactly which regional rainfall is needed to replenish it. Water sources in arid regions are often maintained and passed down orally through generations, proving that social knowledge is sometimes far more critical than current physical signs. The sixth step is opening the source and waiting for the seep. With a soakage, you don't necessarily have to dig down to a massive cavern of water. You simply scoop away the top layer of sand or mud, open a shallow depression, patiently wait for the moisture in the sediment to seep out, scoop away the first muddy batch, and wait for the slow recharge to fill it again. The mechanism here is natural seepage, not a sudden gushing spring. The seventh step is protecting the source. After use, it must be covered up to prevent large animals from trampling and collapsing the walls, to keep waste away from the drinking water, and to give the source time to recover. Finally, the eighth step is carrying the water away. Containers reduce the number of times you have to return, allow you to cross arid stretches, support young children, create stashes, and let the camp sit further away from the water source to avoid fierce survival competition. This mechanism explains how water could be found, but the strongest evidence doesn't come from an intact prehistoric hole in the ground. It comes from geology, recorded indigenous knowledge, ancient containers, and how water points structured an entire continent. Modern hydrologists never start by drilling randomly. They look at rock types, valleys, sediment layers, vegetation, and the relationship between surface and groundwater. The U.S. Geological Survey explains that groundwater resides in saturated zones of soil or rock. Valleys often hold shallower groundwater prospects than hills, and water-loving plants in arid regions can act as indicators for relatively shallow water tables. Alluvial aquifers can hold water winding through sand and gravel deposited by currents. Therefore, a riverbed that is bone dry on the surface doesn't automatically mean the entire system beneath it is dead. Ancient humans didn't need to understand complex scientific jargon like hydraulic conductivity. They only needed to observe which spots stayed damp longest after a rain, which plants only grew on specific soils, which sections of a creek could still be dug into, and which sources recharged quickly. Through countless observations, physics transformed into practical knowledge. However, topography only creates probabilities. Modern landscapes don't reveal every condition of the past. A modern hydrologist looking at a geologic map and an ancient human looking at a mountainside are using different tools, but they are both searching for the exact same thing: where the water converges. In the arid zones of Australia, indigenous communities relied on a vast network of tiny water sources: native wells, soakages, rock holes, springs, and claypans. Many of these could only be found with precise, localized knowledge. Take soakages, for example. These might be places where water sits deep in the sediment, sand obscures the dampness, the opening is completely filled in, and water only pools after someone comes to dig a depression and waits patiently. These sources need to be cleaned, protected from animals, visited in the correct season, and used at a pace that matches nature's ability to recharge them. The Western Australian Museum describes Gnarlbean soak as an incredibly important source for Aboriginal people long before it became a key stopping point for European explorers. Its value wasn't that it was easily visible to a passerby, but that its location was memorized and constantly maintained. The history of the Canning Stock route also records that survey teams coerced Aboriginal guides into revealing water sources. Out of the 48 artificial wells on that route, 37 were built directly on or immediately adjacent to existing Aboriginal water sources. This is the sharpest proof of the difference. A landscape that is completely dry and invisible to an outsider is actually a highly detailed survival network to those holding local knowledge. Hidden water might just be a lack of information on the stranger's part, not a lack of physical traces. Plants and animals act as vital clues, but they are not absolute compasses. Phreatophytes, plants that tap into the water table or the capillary fringe just above it, can help identify relatively shallow groundwater. But a lush green patch of trees all by itself can be completely misleading, as some species plunge roots far deeper than anyone could dig. The same goes for animals. Birds and beasts can help pinpoint a source, but the value doesn't lie in just blindly following a herd. The value lies in specific knowledge. Which species needs to drink frequently, what time they leave the source, whether they are flying toward or away from it, and exactly how fresh that footprint is. A patch of green trees at the bottom of a riverbed, next to a fresh animal track pressed into the mud, located in the exact spot of an old water source from memory, is a far more powerful combination of evidence. Finding water is only half the battle. Survivability isn't just about discovery. It is a chain of actions: find, extract, contain, transport, and remember. Records of adaptation in the Kalahari Desert show that the Sand people utilized small sip wells and stored water in ostrich eggshells. A slow-seeping source might not let an entire group quench their thirst at once. But if the water is extracted bit by bit, transferred into containers, carried along or dispersed into hidden caches, a tiny seep becomes a resource for a massive journey. Without a container, a group is forced to camp right next to the water. With a container, they can choose a better shelter, expand their hunting routes, and move with flexibility. At the Diepkloof site in South Africa, sediment layers preserved hundreds of engraved ostrich eggshell fragments following repeated design traditions, dating back roughly 60,000 years. Deliberate perforations and ethnographic comparisons strongly support reconstructing them as liquid containers. This suggests water-carrying technology emerged very early. Combined with a research model on the distribution of small water points in inland Australia, we see that networks of wells, rock holes, and springs created survival corridors. The empty space between water points is the ultimate barrier. Knowing where the next point lies is the first prerequisite, and carrying enough water to survive the trek there is the second. Invisible water, therefore, exists in two places: beneath the ground and in the memory of the next stop. Geology explains where the water can exist. Indigenous knowledge shows how those tiny points are remembered and maintained. Ancient containers show how humans could stretch their distance from the source. No single element is enough to explain life in arid zones, but pieced together, they form a flawless system. However, finding water was never the end of the challenge. Having water doesn't mean having enough water. A soakage might only seep very slowly, provide just enough for a few people, run completely dry if scooped too fast, or turn muddy if the sandy walls are disturbed. A survival group had to know not just the location, but the actual capacity of that source. Moreover, having water doesn't mean it is drinkable. The water could be saline, stagnant, fouled by animals, tainted with decaying carcasses, or full of pathogens. A rare water source is essentially a piece of social infrastructure. It requires someone who knows its location, someone who can clean it, rules for its use, seasonal memory, limits on how many people can stay, and protection from damage. A tiny hole in the sand turns out to be a collective technology, and because survival depends on it, water can be highly sensitive information. In a harsh environment, knowing the location of a rare source directly affects the freedom of movement, diplomatic relations between groups, and the ability to survive brutal droughts. The biggest twist is that a hidden water source is sometimes safer than an exposed one. Covering a soakage helps reduce evaporation, prevents large animals from trampling it, limits contamination, and keeps it hidden from outsiders. But this very concealment turns it into a lifeline utterly dependent on the transmission of knowledge. When the people who hold the location are gone, the water source can culturally vanish, even though the current still flows beneath the earth. In tandem, water containers completely redrew the survival map. If each person could only bend down to drink at the source, every travel route had to hug the puddles. But when water could be packaged and carried, camps could be set further away, groups could take strategic detours, small sources could be sustainably harvested over time, and the safety buffer between two water points widened. The ability to find and carry water didn't just expand where humans could reach, it expanded the places they had the privilege to choose not to stay. But because water sources could be hidden, cleaned, and constantly reused, the archaeological record easily tricks us into confusing a complex technical system with a perfectly natural depression in the dirt. Despite this, we cannot turn modern hydrological knowledge and indigenous survival models into a universal cheat sheet applicable to all of prehistory. A dry riverbed might simply be a dry riverbed. An alluvial aquifer might hold water, but the water table might have dropped too deep. The sand layer might be too thin, or the old channel might no longer receive recharge after prolonged droughts. There is no guarantee you will hit water just because you are standing at the lowest point of a valley. Plants can also completely deceive an observer. A lush green tree might survive thanks to roots plunging dozens of feet underground, water stored in its trunk, or an extraordinary biological tolerance to drought. Only those with precise knowledge of local flora can make a useful judgment. Animals aren't absolutely reliable guides either. Their tracks might be heading toward a feeding ground, walking away from water, or leading to muddy wallows completely unfit for human consumption. Data from Aboriginal or Sand people aren't transparent windows looking straight into the Paleolithic. These communities have their own histories, languages, territories, and have experienced profound disruptions. Their survival methods prove that a knowledge system can work effectively, not that our distant ancestors did exactly the same thing down to the last detail. In archaeology, a small hole in the ground is incredibly difficult to confidently identify as a water well. It could be a post hole, a cooking pit, or a natural erosion hollow. Even with ostrich eggshell flasks, while their shape and wear marks support a liquid container function, we cannot confidently claim every single fragment held fresh water for a massive migration. The evidence shows humans could read the terrain, use seepage sources, pass down knowledge, and carry water away. But it does not allow us to draw a single water-finding method for every place and every era. Even though modern tools offer deeper and more precise testing, we still start in the exact same place, observing how water, soil, plants, and topography are intimately connected. Modern hydrologists today also survey low-lying topography, permeable rock layers, alluvial sediments, outcrops, and groundwater-dependent vegetation. These observational layers intersect perfectly with ancient practical knowledge. Even equipped with geophysical instruments, exploratory drilling, chemical analysis, and satellite data, modern science shares a fundamental baseline with the past. However, indigenous knowledge isn't just dry physical observation. It is tightly bound to place names, traditional routes, seasonal calendars, access rights, rituals, and the responsibility to care for the water source. It would be wrong to say ancient humans were accidentally doing hydrology. A more accurate way to put it is, humans across all eras have built different knowledge systems around the exact same physical reality. Water always leaves a trace, even when it is hidden from view. A data point is only truly useful when it is accurately located, remembered, constantly updated, and trusted by others. That holds true for a soakage in the desert, a measuring station, or a state-of-the-art satellite mapping system. The two maps of the past and present might not look the same, but together they accomplish what no stranger ever could, turning a barren wasteland into a network of life. So when we return to the waterhole from the opening, the most important thing isn't the moment the water appeared. It is the entire chain of observation and memory that led that person to choose exactly 1 square meter out of miles of dry dirt. Back to the dry riverbed. The water continues to seep out slowly. The group doesn't view this as a miracle. The signs were logically decoded. A valley that gathers runoff, a bend that catches sediment, plants that indicate moisture, animal tracks confirming recent activity, and above all, the memory that pinpointed the exact location used by those who came before. The water is scooped up in small amounts. Some quenches their thirst, and some is carefully transferred into portable containers. The whole is then covered up, preserved intact for the next use. The group continues their journey, heading toward the next known water point on their mental map. Humans found invisible water by identifying where the landscape was likely to gather and hold it, like valley floors, old riverbeds, sand and gravel sediments, and rock crevices, and then combining those signs with animal activity and precise knowledge of previously used sources. No single clue guaranteed success. A riverbed could run dry, roots could plunge too deep, and animals could lead them astray. The difference between life and death lay in multiple clues confirming a single spot, and the memory of knowing exactly which season that source would provide. A modern human's map usually only shows what is plainly visible, rivers, lakes, or wells. But a survival map from the deep past held water under the sand, sources that only existed right after a rain, rock holes that needed to be cleaned, or spots where you had to patiently wait for a seep. People found invisible water by learning to see the visible traces of where water had moved, gathered, and survived. The group slowly leaves the riverbed. A gust of wind sweeps the sand, covering the traces of their digging. The ground once again looks completely bone dry, but now, hidden beneath that sand is no longer emptiness, but the contours of a catchment, the slow pulse of life, and a long trail connecting the living.